Ladies and gentlemen, good day. My name is Hamza, and I am delighted to stand before you today to present my research on the integration of digital twins and smart urban lighting. During my internship with the esteemed LAPLACE lab, I have had the opportunity to delve into this fascinating topic, exploring the potential benefits and implications it brings to urban lighting systems. Our study revolves around the crucial issue of street lighting, with a specific focus on the long road of the highway. But before delving into the integration of digital twins and LED lighting, it is essential to understand the significant challenges that plague highway lighting systems. Highway lighting systems often confront a myriad of problems that demand attention. Bulb outage, damaged fixtures, inadequate lighting energy inefficiency, light pollution, inconsistent lighting and lack of maintenance, and this can lead to feared disasters. Digital twins have emerged as a powerful tool that allows us to bridge the gap between the physical and digital worlds, unlocking new possibilities and revolutionizing how we design, operate, and optimize systems. So, what exactly is a digital twin? In simple terms, a digital twin is a virtual replica or simulation of a physical object, process, or system. It is a digital counterpart that mimics the behavior, characteristics, and performance of its physical counterpart in real time. This virtual representation enables us to monitor, analyze, and manipulate the system in ways that were previously unimaginable. We can run tests and get results without any risk or expenses. Digital twins can be broadly categorized into two main types: the digital twins prototype, DTP, and the digital twin instance, DTI. The digital twins prototype serves as a communication tool between product developers and end users, facilitating collaboration from the initial idea and design phase to the commissioning stage. It allows stakeholders to visualize and evaluate different design alternatives, simulate real-world scenarios, and gain a deeper understanding of how the physical system will perform. By connecting the digital twin to the physical entity through the Internet of Things, IoT, and live sensor data, the DTP becomes a platform for testing and validating ideas before investing resources in physical production. On the other hand, the digital twin instance contains data related to real-time operating conditions captured by sensors, historical and predicted states, as well as warranty information. It provides a comprehensive representation of the in-use conditions of the physical system. The DTI acts as a virtual mirror, reflecting the behavior and performance of its physical counterpart. By continuously monitoring and analyzing data from the DTI, we gain insights into system performance, identify inefficiencies, and make informed decisions. Let's discuss the fascinating world of smart lighting. This innovative concept aims to revolutionize our domestic lighting systems by allowing users to control and manipulate their lights remotely through a mobile application. With just a few taps on their smartphones, users can adjust the intensity, frequency, and timing of the light according to their preferences and needs. However, the smart lighting project is not without its challenges. In fact, there are two critical aspects that need to be addressed: the seamless transition between the on and off states and the ability to smoothly adjust the light intensity. These adaptations should be tailored to the specific requirements and demands of the users. Moreover, achieving energy efficiency is a key objective of smart lighting. This entails the capability to detect daylight and automatically adjust the lighting intensity to avoid unnecessary power consumption. Additionally, the ability to control the emitted heat flux by providing varying levels of light gradation is essential for both interior comfort and personal preferences. To realize these functionalities, real-time interpretation of controls and analysis becomes paramount. The data generated by the system should be processed and responded to instantaneously to ensure a seamless user experience. Furthermore, careful consideration must be given to space management when dimensioning the luminaires, as the placement and arrangement of the lights play a significant role in the overall effectiveness and aesthetics of the lighting system. The creation of a DT involves using sensors to collect data from physical systems in the real world. These sensors measure physical parameters like temperature, pressure and motion and convert them into digital signals thanks to their internal structure, for example, polarizer, magneto-optic crystal, prism. The signals are then transmitted to a microcontroller, which processes the data, applies calibration factors and produces an output signal that can take the form of a binary form or a more complex digital signal, depending on the time of data being measured. The calibration is mostly prepared in the lab beforehand and can be modified easily during maintenance time. The microcontroller, then, transmits the output signal to software that creates the digital twin via an custom server. We may also collect information to the digital twin from an old system's data and use it to create an ameliorated system. For the creation of a DT for street lighting, sensors and controllers play two important roles. The sensors collect data from the luminaire and its surroundings and send it via microcontroller to the DT, then the controllers act on the luminaire using commands sent from the DT. By implementing such a system, we can effectively mitigate common issues associated with traditional street lighting, while achieving greater energy efficiency and cost savings. However, it is important to note that the degree of energy savings achieved will depend on a variety of factors, including the size of the lighting system and the amount of daylight in the area. As such, a comprehensive street optimization plan is necessary to ensure optimal results. In general, a single DT server can control and monitor anywhere from a few dozen to several thousand lighting poles, depending on the specific system design and application. However, it is important to note that adding more poles to a DT system may increase the complexity of the network and require additional resources, such as data storage and processing power. According to Philips, the City Touch server can support up to 200,000 connected devices, which includes luminaires, lighting control nodes, and other devices. However, the number of poles that can be connected to a single server can vary depending on factors such as the configuration of the system and the specific needs of the project. When developing a digital twin, you may need to write code for both the microcontroller and the DT, digital twin, server. The microcontroller code is responsible for handling the interactions between the physical system and the digital twin. It involves programming the microcontroller board with instructions that allow it to collect data from sensors, process that data, and transmit it to the DT server. The microcontroller code typically runs on a firmware level and is written in languages such as C or C++. On the other hand, The DT server code is responsible for managing the digital twin itself. It involves creating the virtual model, receiving data from the microcontroller or other data sources, analyzing and processing that data, and providing insights or feedback to the user or other systems. The DT server code can be written in various programming languages, depending on the platform or framework you're using, such as Python, Java, or C#. It's important to ensure proper communication and synchronization between the microcontroller and the DT server. The microcontroller code should send the collected data to the DT server using appropriate protocols or APIs, while the DT server code should be able to receive and interpret that data accurately. Additionally, the microcontroller code may also include control algorithms or logic that enable the physical system to respond to commands or adjustments made in the digital twin. This allows the digital twin to have an impact on the physical system, creating a closed-loop feedback system. In this part, I want to highlight the incredible impact of LED technology on street lighting. LED lights offer numerous benefits that are transforming our cities. LEDs are highly energy efficient, reducing costs and lowering our carbon footprint. They have a long lifespan, requiring fewer replacements and reducing maintenance expenses. With their exceptional brightness, LED lights enhance visibility and safety for pedestrians and drivers. LED technology provides flexibility and control, allowing for dynamic lighting adjustments to meet specific needs. Moreover, LEDs contribute to a visually appealing urban environment, creating a welcoming atmosphere. In summary, LED lighting is revolutionizing street illumination, making our cities safer, greener, and more visually appealing. In order to determine the perfect LED lighting system for a lighting pole in a highway, we need to follow a number of steps. First, determination of the area to be illuminated. Second, determination of the required illuminance level. For highways, the recommended illuminance level is typically 30 lux. The required luminous flux can be calculated then 7,200 lumens. Third, determination of the mounting height. The mounting height of the LED fixtures will depend on the specific application and can be determined based on the required illuminance level, 30 lux for urban roads, and the characteristics of the LED system. In this situation we have 12 meters. Fourth, D. Determination of the beam angle of the LED fixture. The beam angle of an LED fixture determines how the light is spread out from the fixture. In the context of a highway lighting application, it's important to focus the light more towards the road surface to ensure proper visibility for drivers. Therefore, a beam angle of 60 degrees may be chosen to achieve this goal. Finally, the selection of LED system that can meet the previous specifications. In this application we are going to modelize one highway street with the digital twins LED solution. Our study assumes a spacing of 40 meters between each pole, which would require approximately 25 poles for a 1,000 meter street. The poles will be classified as normal poles, toggled with state sensors, or special poles. The first special pole is the one that turns on the light of the whole street as it receives information about passing cars through its motion and movement sensor, while the second special pole turns off the light of the street using daylight sensors in addition to motion sensors. This study shows promising results. The DT LED solution emerges as the most advantageous choice for street lighting systems. It offers significant energy savings, improved functionality, enhanced control, and lower overall costs, and we can see it clearly with the light quality provided and the user-friendly attitude along with reduced energy consumption, 86%, and economy, 47%. By combining digital twin technology with LED luminaires, cities can achieve efficient and sustainable lighting infrastructure.